Okay, we're going to, one of the issues with senior secondary school physics is that we really only get up to the end of the 19th century. A lot of what we do is not modern physics. It's physics that's been around for quite some time. But for this last module and the last part thereof, we're going to spend a bit of time looking at modern physics. So 120 odd years ago, I guess, there are quotes from physicists saying, we're really pretty much, there are only a few little corners to chase up, a few little wrinkles, things we haven't quite explained yet, but we've pretty much finished the project of physics. We can pretty much all knock off and go home pretty soon because there aren't too many problems left to solve in the real world. One or two of these minor little edges and niggles and issues that were arising. One of those was the photoelectric effect. And in a couple of weeks when we talk about quantum, we'll find out what happened when a young physicist, and he was a physicist, people tend to pretend that he was a student or that he really hadn't done much study, but young physicist named Albert Einstein, who was making ends meet by working in a Swiss patent office, made of the photoelectric effect when he investigated it. In a particularly spectacular year, 1905, when he published a paper on Brownian motion that got him quite a lot of attention, and then papers on relativity and quantum that actually moved us on some considerable distance. So we'll talk about the photoelectric effect when we talk about quantum in a couple of weeks. But something else that he did was work on relativity as well. So quantum actually, I think, might be 2 weeks away rather than next week, but no, it is next week. And then the week after is radioactivity, nuclear energy, and all of that fun stuff. So yeah, okay, quantum is real soon. So as I say, Einstein tried to solve a couple of these problems. One of the things that's kind of interesting, I think, is that Einstein clearly was unbelievably influential. He had a huge year in 1905 and another huge year in 1915. He then lived a long and fruitful life and did a lot of interesting work, but a lot of it also ended up not being productive paths that he was following. It's interesting and worthwhile work. You might remember some considerable time ago, I said that Newton had a great flowering in his youth and then went off into what seems to us to have been unproductive work in the rest of his life. It's possible that Einstein suffered, followed a similar path in a way, did some great stuff in his youth, and then either his celebrity and everything else meant that he did work that wasn't as effective, or he went off beyond to the point that we can't follow him. So that might be interesting to go forward. In some ways, we kind of feel like we're a long way further, but there are still many little niggles and issues. In fact, there are a lot more. I don't think any physicist would now say, well, we're just about at the end of physics. They would say, we're just at the beginning. There's so much we don't understand. And we're due another Einstein. We're due someone to come along and make a huge revolutionary change. A number of people have tried it over the years and have made great contributions, but there hasn't been somebody at that towering level of a Galileo, Newton, Einstein for a while. So maybe one of your students, maybe you'll light the fire, light the fuse that causes the next massive revolution, because really both quantum and relativity revolutionized the way we understand the world. So relativity, we talked about relativity. Galileo really talked about the fact that the Earth is in motion, that all motion is relative, that there is no absolute still point. So the notion of relativity in that sense just means that there is no one defining reference frame that we can use that we can refer all motion to. We can't even decide that the universe is an overall stationary reference frame because everything in it is moving relative to everything else, and the universe itself is expanding. So where would we decide is up, down, left, right, front, back? What is that stationary? There really isn't. So we can only ever talk about motion as being relative to other motion. So it's all relative in that sense. We choose frames of reference convenient for our purposes. Like when we were talking about energy, we typically decided that if we're dropping a stone to the ground, then the ground is going to be our 0 point for energy, and this will be our plus mgh point for energy. Right? We chose a reference frame that makes sense for us. We could as easily have said this is 0 energy, and then we drop it to the ground and it's minus mgh joules, because it's relative. There's no absolute point. The ground goes up, goes down, is different at different places and so on. It's not the absolute 0. It's not very convenient to talk about the center of the Earth, as the absolute 0 of gravitational potential energy around here, because I'm dropping it through 1 meter. The distance to the rest of the way to the center of the Earth is 6.4 million meters. So my little drop is going to be completely irrelevant drop in the bucket compared to that 0 point. So it's not convenient. So we choose convenient frames of references for our purposes at particular times and in particular problems and issues. So Einstein first developed special relativity. He developed it through a thought experiment. He describes trying to imagine what it would be like to be a particle of light or a ray of light traveling around the universe under a whole variety of different situations, and exactly how that would be. So there's an Einstein quote that you'll often see on t-shirts, which is, imagination is more important than knowledge. And his own process was to imagine first and then do the maths. It's easy for anyone to imagine, but the second step is the step that actually gets you famous, is being able to do the maths to back up that imagination. So he actually drew on some earlier work by Lorentz and others around the relevant mathematics in different reference frames, and created the theory of special relativity. It always used to kind of bug me that special relativity was the worst one and general relativity was the best one, or the most powerful one, put it that way, because it sounds like special is special and general is just general. But in fact, it's special in the sense that it only applies to a special set of circumstances. It's limited, it's narrower, it's specialized, right? Whereas general relativity is more powerful because it's more general. So that's the distinction between special and general relativity. And they treat of different things. General contains special, but it expands beyond it and continues to other places. Special relativity assumes that there's no privileged reference frame, including moving reference frames moving relative to others. Einstein's big step was to say the speed of light must be constant for all observers, no matter how they're moving relative to each other. So if a light is on a train that's going past me at 0.9 of the speed of light, I won't see the beam of light out at the front of the train going out at 1.9, because it's going out at 1 times the speed of light because it's light, and another 0.9 because it was already traveling at 0.9 relative to me. Does that make sense? So in other words, the speed of light I will still see it as going forward at 1 times the speed of light. No matter what reference frame I'm in and how I'm moving relative to other reference frames, I will see the speed of light as being constant for all observers. If you do that, and I've just mentioned here, the syllabus doesn't require it. It involves a lot of square root of 1 minus v squared over c squared, where v is the velocity of the thing itself and c is the velocity of light. So that particular factor crops up a lot. It is Lorentz's maths, but Einstein used it. And it's quite helpful, because what you actually do once you get into the maths, once you start doing the calculations, you discover that if this is going to be true, if the speed of light is going to be constant everywhere, then something else has to give. And it turns out that mass, length, and time give. That as we get closer to, and you may be familiar with this already just from popular science contexts or from your own reading and so on, as we get closer to the speed of light, length contracts in the direction of motion. It doesn't change in the direction perpendicular to the motion, but in the direction of motion, length contracts. Time contracts as well. Time travels differently when you're moving at great velocity. And mass increases. As you increase your velocity, your mass increases until it would become infinite at the speed of light. So that's one of the reasons that you can't go faster than the speed of light. The notion of the speed of light as an absolute speed limit for the universe is partly about that you would have an infinite mass, and you would therefore require an infinite force to accelerate it. And clearly, if you don't have anything that's going to provide an infinite force. Another way of thinking about it is you would use all of the energy in the entire universe to accelerate that last tiny bit to hit the speed of light. Now, light itself can travel at the speed of light because it doesn't have mass. Light, photons, are basically intertwined electric and magnetic fields that mutually reinforce one another. So light travels at the speed of light, but nothing in the universe can travel faster than the speed of light. You'll remember a couple of years ago, there was great excitement because it seemed as though neutrinos in Italy were traveling faster than the speed of light. At the time when that news came out, I said, hey, that would be incredibly exciting if it's true, because it would be the beginning of a scientific revolution. But I was quite skeptical, and it turned out that I was right to be quite skeptical. It was an error in their equipment, and there was some time being introduced somewhere along the line that meant, in fact, no, the neutrinos were not going faster than the speed of light. We haven't yet observed anything to travel faster than the speed of light. That seems to be the ultimate speed limit of the universe, and there are reasons why that's the case. Length contraction and time dilation are kind of interesting as well. So I've mentioned here, if twins were separated and one traveled at close to the speed of light, let's say they go out to Alpha Centauri and back. So Alpha Centauri, our closest star system, the Centauri star system, if someone traveled from here to there, it's about 4.3 light years away. So it would take 4.3 years for the light to travel from there to here, but it would take much longer for a ship. So if you accelerated all the way at 1g, so you didn't squish yourself by too much acceleration, and then decelerated for half the trip, and then accelerated and then decelerated, I think it takes about 40 years to get there and back. So 4.5 light years there and back, so 9 light years there and back. But it takes about 40 years to actually make the trip because you have to accelerate and decelerate. You're not light, you can't instantly go up to light speed. If someone did that, the time that passes for her, the person that's in the spaceship, and the time for her identical twin on Earth would be different. And in that 40 years in the journey, something on the order of 400 years, depends quite on the details of the speed attained and so on, something on the order of 400 years would have passed on Earth. So the twin remaining on Earth would probably no longer be around and have great-great-great-great-grandchildren, while the person who had traveled out and back would be only 40 years older. This is very weird and unintuitive, and this is part of what is cool but also difficult about modern physics. Both relativity and quantum are very weird, very difficult to understand, very unintuitive. So getting students to understand them is often quite challenging. But this actually is the case, and this has been measured. As I may have mentioned earlier, it took a while for it to be measured because you needed atomic clocks and you needed fast planes high in the atmosphere. But once it was measured and tested, yes, time does actually dilate when you're traveling at some fraction of the speed of light. We know this. And in fact, there's another really cool example, which is that you get certain solar radiation that hits the upper atmosphere and creates particular muons. And those muons come from the upper atmosphere. Don't worry about what a muon is at the moment. It's not particularly relevant for the purpose of the story. Come down and hit the surface. Now, those muons have a very short lifespan, on the order of millionths of a second. If time was normal for them, they wouldn't get to the surface because they would be created in the upper atmosphere and disappear before they got to us. But because they're traveling at the speed of light, time is dilated for them, so they do actually make it all the way to the surface. Time is different for them compared to us because they're moving at the speed of light. So there's lots of experimental confirmation of this stuff. It's not just something that Einstein came up with dreaming under a tree and created some maths for. It's true. It's empirically the case that this happens. One of the things about the speed of light being a limit is that, as I say, it takes 40 years to get to our nearest star system. We now know something that we didn't know even 10 or 15 years ago, which is that there are lots and lots and lots of planets out there, and quite a few of them have the potential to be inhabitable. That is, they are the right distance from their sun, and their sun is at the right stage of its life to have liquid water on the surface. Now, they might have all sorts of other toxins or other extreme conditions and so on. Our Earth is incredibly nice for us in terms of the seasons and a whole variety of other factors that make it good for our particular life form. That's getting to be a long story, but Alpha Centauri doesn't have any of those habitable planets. The nearest star system with some might be 9 or 10 light years away. So it's going to be, at the absolute minimum, it's going to be hundreds of years before we can actually travel to those. So almost all of your science fiction has had to cheat with this. So they talk about warp drives or faster than light drives or a variety of different ways of cheating this, going through wormholes, because you can't have a galactic empire if it takes 100 years every time you want to go down to the shops, every time you want to go to the neighboring inhabited planet. We could do generation ships. So have a ship big enough that you can have enough people on it that they can be born, live, give birth to the next generation and die on the ship. Now there's ethical questions about that. Is it fair for us on a planet to create a situation where some people will never get to experience a planet? They'll always be living on a ship all of their lives. Really interesting questions, but at the moment, unless we do invent some kind of faster than light drive, we are quite limited in terms of where we can get to around the universe, and so are aliens, right? The idea of alien attacks and encounters, friendly or otherwise encounters, I guess, seems quite implausible, even if there are lots of aliens out there, simply because space is big. As Douglas Adams put it in Hitchhiker's Guide to the Galaxy, if you think it's a long way down to the shop for a packet of peanuts, that's nothing compared to space. But yeah, space is vast and the speed of light appears to be the limit, unless the aliens figure out a way to beat it that we haven't figured out. So it's quite possible that there could be a galaxy, a universe full of alien species, but we'll never hear from them because they're just too far away. Anyway, that's kind of a fun, I hope, but a bit of a digression. The other consequence of special relativity is that it treats space and time largely the same. It says that we live in a four-dimensional universe, 3 space dimensions, up, down, left, right, front, back, or however we want to label those dimensions. We have 3 dimensions of space and 1 dimension of time, and we're traveling forward through time. Now we can move freely in the space dimensions. Moving in the time dimension is harder, but we've just been talking about the fact that if you go fast enough or do various other things, you can move in the time dimension. So we can time travel. Everything that we know at this stage says that you can only travel forward, never backward. So again, you can't do that science fictional thing of, well, we'll go to the future, find out their technologies and bring it back. Or we'll go back to the past, kill Hitler, come forward again. As far as we can tell at the moment, time travel to the past is impossible, but time travel to the future is possible. So that's kind of fascinating, but that's interesting. Why is the arrow of time as it is? Well, you might have read, or at least purchased, because a lot more people purchased than read, Stephen Hawking's little book, A Brief History of Time, which talks about the arrow of time and why we go forward through time rather than backward. So a couple of other contributions from Einstein as well before we get into general relativity. E equals mc squared, probably the most famous equation of all, not just Einstein's most famous equation. The equivalence of mass and energy. So not only have we got space-time, we talk about the space-time continuum. It's those 4 dimensions of space and time. We also have matter-energy, because they're really the same thing. They're interconvertible. If you convert an energy to a mass, but there's that multiplying factor of c squared, the speed of light squared, 3 times 10 to the 8 meters per second, squared is 9 by 10 to the 16 meters squared per second squared, right? That's the actual conversion factor, which is vast, 10 to the 16, one with 16 zeros after it. So a very small amount of mass will produce a very large amount of energy. The atomic bombs at Hiroshima and Nagasaki that we've just been commemorating the anniversaries of fairly recently probably converted a couple of grams of uranium or plutonium into energy, and that was sufficient to destroy a city. So that conversion factor between mass and energy is huge, but matter we can talk about matter energy as one thing and space-time as one thing. If we've got those two concepts, matter energy and space-time, then we're ready to start talking about general relativity. So general relativity, Einstein came up with special relativity about 1905, general about 1915. He didn't actually get his Nobel Prize until 1935, partly because it took a long time for physics to catch up with how far he'd leapt, how quickly. We're going to talk all about quantum next week, which he didn't develop alone. There were a bunch of people, Planck and Bohr and Fermi and Dirac and Schrödinger and Heisenberg, who all had a contribution to make to quantum. But Einstein came up with some of the big leaps and advances in that as well. I'm trying to avoid making the quantum leaps pun. Because all reference frames are relative and we can choose our own reference frame, you can't actually tell whether something is accelerating due to gravity or accelerating due to some other kind of force or because of the shape of space-time. So Einstein again asked, does a planet orbit the sun because there's this attractive force? So Newton's theory of gravity, F equals g m1 m2 over r squared, says there's a force between the two and that's why it orbits. Einstein's theory of general relativity says the planet, the Earth, thinks it's moving in a straight line, but space-time itself is curved. So it's moving in a straight line in curved space. So that, in a nutshell, is general relativity. And because of relativity, because every reference frame is equally valued, I guess, we can't have a privileged reference frame. We can't tell between whether it's a force or whether space is curved. And it turns out that talking about curved space-time actually has some other benefits. So general relativity is a description of gravity, but it's a description that actually is more powerful. It will work around things like black holes, where the gravitational conditions are very extreme. It'll work in contexts where Newton's theory of gravity breaks down. But Newton's theory of gravity is quite adequate for all of our everyday purposes. It's only these extreme environments where we need to move to Einstein. So we don't actually replace one theory with the other. One theory is better, more powerful, more general for particular contexts than the other, but they're both useful. So you might have heard this again in popular science shows and so on. Space tells matter how to move. Matter thinks it's moving in a straight line, but in fact may be moving in a curve because the space itself is curved, and matter tells space how to curve. So we should technically really say space-time tells matter energy how to move, matter energy tells space-time how to curve. That's a little bit more cumbersome to say, but that's the more accurate version. So there is this interrelation between space-time and matter energy. Concentrations of mass, like suns, planets, and so on, cause the space around them to curve. So the space-time itself is curved around any mass, including my mass, your mass, the mass of an apple, but obviously much more curved around a large mass. So our sun, or our Earth, our sun, the galactic center, or a very big sun. If you get a chance, go on YouTube and search star size comparison. There are about 4 or 5 videos of star size comparisons that start with either Earth or the sun and then show you in very graphic form how big some stars are. So some stars are vastly, 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 vastly bigger than our sun. So that's a really nice, quite sobering sense of our size in relation to the rest of the universe. Although the videos tend to end up by saying it shows how small we are. And I don't agree with that because it's relative, right? We are also vastly bigger than a quark or a subatomic particle. So we're the size we always were. We know now that the universe is much bigger than we thought it was. We know now that subatomic particles are much smaller than we thought they were. But it doesn't mean we're small. It means that we know more, which is a good thing. One mass curves the space-time and the other mass follows the curve, but it in turn is also curving the space-time. So there's one of the things that's often used to imagine this is a rubber sheet. So if you stretch out a rubber sheet and then place a mass on it, it makes a well. And then if you roll another mass along the sheet, it will travel in a curve around that well. Now that's a two-dimensional analog of a three-dimensional space, four-dimensional space-time, right? So it's not perfect, but it's a nice way of getting it into our head. But you'll also notice that the small mass is itself denting the rubber sheet as well. So the big mass is making a bigger dent in space-time, the small mass is making a smaller dent in space-time, and those things are interacting. So the space-time around them is quite complicated. If you think about the fact that we have the 9/8/9 planets in our solar system, I think we have Pluto back, according to the astronomers now. And there are potentially a couple of other small planets or dwarf planets around as well. If you think about all of those, and then their many, many moons, they keep finding more moons for Jupiter and Saturn and some of the bigger planets. The space-time in our solar system is incredibly complicated. You've got lots and lots of things spinning around each other on their rubber sheet, each of them disturbing the matter of the shape of space-time. So general relativity describes that. Clearly there are equations. I'm giving you the qualitative version, the descriptive language version. There are equations that describe all of this, but it's hopefully helpful that we kind of understand where gravity comes from and how it interacts with matter. But I said it's space-time that's being curved. So not only is the space curved, but the time is curved. So time passes at a different rate when you're near a big mass and when you're far from a big mass. So when you're close to the event horizon of a black hole, for example, certainly some of the solutions of the equations suggests that you can never actually go into a black hole. The Disney movie to the contrary. But as you get closer and closer to the event horizon, time slows and slows and slows. And the amount of time to go through the black hole, the event horizon and inside the black hole would be infinite, because time would have stopped for you just outside the event horizon. Now, you would also have been ripped to pieces by the gravitational tidal forces, because the difference in gravity between your head and your feet would be so extreme that you'd get ripped into tiny pieces. So don't go flying into any black holes. Bad idea. Also impossible. So anyway, time passes at a different rate. So out in interstellar space, time passes faster. Closer to big masses, time passes slower. So, and again, we've observed this. And it was kind of interesting to think about which effect would predominate for the astronauts who traveled to the moon, because they were going quite fast. They were going 50,000 kilometers an hour, which is a small but not insignificant fraction of the speed of light. So would time pass more slowly for them because they were traveling close to the speed of light? Or would it travel more quickly for them because they were further away from Earth and its gravitational field? It turned out that it was the special relativity that predominated over the general relativity, and they probably have a few seconds, maybe a few milliseconds, on the rest of us who stayed here on Earth. It was a very tiny effect, but it was an interesting one to think about which of those effects predominates. It's interesting to think about our twins who go to Alpha Centauri and back, which of those effects will predominate, because they will be much further from the gravitational field of a particular solar system. So I've mentioned that the experimental tests we have for general relativity all work. We have tested it. It's real. It's a thing. The tricky bit, and this is what we get into next week, is that general relativity works really well at the big scale. The scale of planets, suns, stars, scale of us works perfectly, explains everything, predicts what's going to happen, describes. At the micro subatomic particle scale, general relativity doesn't work at all. Quantum works. And quantum doesn't work at our scale. I'll talk quite a bit about that next week. So this is, if you like, this is the photoelectric effect of physics at the end of the 20th, beginning of the 21st century, is this fact that we have quantum at the micro level, general relativity at the macro level, and they don't really meet. And I mentioned that Einstein had been off doing unproductive stuff. What he was doing was searching for a grand unified theory that made sense of everything at all scales. It's the holy grail of physics. It's often called the GUT, Grand Unified Theory, or GUT. And you know, the person who made it, who creates one, will be the next Einstein, for sure. It's a huge deal. But for the moment, we just have to say quantum scale, classical scale. So classical scale is everything bigger. Quantum scale is the really tiny stuff. And that's what we're going to talk about next week.